Okay, good afternoon, everyone. So it's the 11th week. We are meeting for the course uh, Fluid and Particle Mechanics. So in this course, in this week, I will mainly solve few assignment problems which will help you in final end sem exam. So okay, let me directly go to the assignment problems and then we'll see. So as you can see, so this is assignment 11. Okay, so what it says is that it says that consider an elbow duct as shown in figure. So it draws an elbow duct. So let me also draw it for the sake of clarity. It will help us also later. So okay, so I have an elbow duct of varying cross section. As far as I understood from the figure, the cross sections is also varying. Okay, so it's giving a velocity profile here and a velocity profile there. So this is more or less a parabolic velocity profile, and this is more or less a turbulent velocity profile. Fine. This angle is 30 degree. And it is given this velocity profile at the inlet and at the outlet. The velocity profiles at the inlet and at the outlet are given. Okay, the inlet, so this is section 1 and this is section 2, let's say. Okay, so d1 is equal to 10 centimeter, means 0.1 meter, and d2 is equal to 6 centimeter, means 0.06 meter. Okay, so it is given that consider an elbow duct as shown in this figure, a liquid of density. So density of the liquid is 790 kg meter to the power minus 3, and viscosity, the dynamic viscosity mu is equal to 200 into 10 raised to minus 3 Pascal second. Okay, and the flow rate is flowing through the duct at a rate of this. So flow rate is given as 0.05 meter cube second units. So these are the data which are given there. So so let us then, so this is how the problem look like. Okay, so the first question which they asked is the average velocity at the section 1. So let me go one by one. Okay, so the average velocity V average 1 is equal to Q divided by 5 by 4 d1 square 0.05 divided by pi by 4 into 0.1 square, which is equal to 6.366 meter second inverse. Average velocity at section 2 Q divided by pi by 4 d2 square 0.05 divided by pi by 4 into 0.06 square, which will come something around 17.684 meter second inverse. Problem number 3 is the Reynolds number at section 1 or the Reynolds number at inlet. And let's say this is RE1. Okay, rho V average at section 1 D1 divided by mu. So what is that? So it is 790 into 6.366 into 0.1 divided by 200 into 10 to the power minus 3. So this is something around 2514.57. This is the Reynolds number at section at the inlet section. Reynolds number at section 2. So let me go back to the problem. So the Reynolds number at section 1 is in between 2000 to 3000. Yeah, and now I have to get the Reynolds number at section 2. Yeah, so the average velocity at section 2 I know. Yeah, so the Reynolds number, now I will go back to the Reynolds number at section 2. That is the question number 4. Question number 4 is the Reynolds number at section 2. So this is the Reynolds number at outlet. Let's say that is at RE2. Okay, I'm calling it as RE2. So rho V average at section 2 into D2 divided by mu. Okay, so what is rho? 790 into V average equals to 17.684 into D2 is equal to 0.06 divided by 200 into 10 to the power minus 3, and this is nearly equal to, so let me calculate it for one last time. So this is 790 into 17.684 to 0.06 is the diameter, 6 centimeter. Fine, is equal to this. Okay, divide by 0.2. The dynamic viscosity of the fluid is 200 millipascal. Okay, is equals to 4191.108. 4191.11. Okay, so let me check the answer. So at section 1 the velocity is in between 6 and 6.5. I got 6.366. Velocity, average velocity at section 2 is 17.684. I got it right. The Reynolds number at the inlet is 2514 within 2000 to 3000. The Reynolds number at outlet I got 4191.11. Here the range is in between 7000 to 8000. I think that is something is wrong there in the option. Okay, now go back to, now let's move to question number 5. So what it says, assume that the flow rate is laminar at the entrance. As you can see that the Reynolds number at the inlet is 2514, like just cross the critical Reynolds number. So it will not be a bad approximation if we assume that the velocity profile at the inlet as a laminar velocity profile, which is of the form that V1 is equal to V average 1 into 1 minus R square by R1 square. Okay, where R1 is the radius at section 1. Okay, but I don't think it will be V average at 1, it will be V max. So actual velocity profile for this thing for laminar flow through pipe is V1 is equal to V max. So it will be V max at section 1 into 1 minus R square by R1 square, and the turbulent velocity profile will have the similar form, V max at section 2, V max at 2 into 1 minus R by R2 the whole raised to 1 by 6. So this is the two velocity profile which is given at the inlet and the outlet. Okay, now they are asking what is the momentum correction factor at the inlet, the momentum correction factor at the outlet. Okay, so the momentum correction factor is equals to the actual momentum divided by the momentum based on the average velocity. Okay, that is how we calculate the momentum correction factor. Okay, and so momentum correction factor at section 1. is beta 1 is equals to 1 by area into integration over the, so area is the cross sectional area, into into V1 divided by V average at 1 square into dA. This is how we can write the momentum correction factor at section 1. So what is V average? So given that V1, so what is Vmax? So it is Vmax 1 into 1 minus R square by R1 square. So in Vmax in pipe flow is equal to 2 into V average. 2 into V average at 1 into 1 minus small r square divided by capital R1 square. That implies V1 divided by V average at 1 is equals to 2 into 1 minus R square divided by R1 square. That is what I get. Thus beta 1, so what is the area at section 1 is equals to pi R1 square, right, into, so I'll integrate it, integration 0 to R1, okay, so V by Vmax square equals to 4 into 1 minus R square small r square divided by capital R1 square whole square into elemental surface area is 2 pi r dr. Am I right? Yes. So what is that I am getting from here? So from here I get that this, so pi cancel out, 2, 4, that is 8. Am I right? So this is 8 divided by capital R1 square into integration 0 to capital R1 into 1 minus small r square divided by capital R1 square the whole square into r dr. What is that integration here? Okay, what will be this integration here? What will be this integration? I think this integration will turn out to be R1 square by 6. Okay, those integration will turn out, this integral will turn out to be R1 square by 6. So integration 0 to R1 1 minus r small r square divided by capital R square whole square r dr is equal to R1 square by 6. Okay, so these we need to so this integration is something which we are using it here. So okay, so what is that? That means this is 8 by 6, 4 by 3 is equal to 1.33. Fine. I guess this is fine. Okay, now momentum correction factor at section 2, which is the question number 6. I guess it should be the the momentum correction factor at the outlet. Okay, so the momentum correction factor at outlet is beta 2. So this beta 2 is equals to integration 1 by pi r2 square into integration 0 to r2. Okay, what is the velocity profile there? So v2 by vmax. So let's say here I'll assume one thing, that okay, let us assume that like v average at section 2 or rather the v maximum at section 2 is some constant c into v average at section 2, where c is definitely some positive constant. We don't know that. Okay, so this c is some constant greater than 0. Okay, so what will be there in my integration? So the velocity profile is 1 minus this by this, so vmax, there will be c coming here, so there will be c square, and then it is the square of the entire quantity, so that means 1/3. So this will be 1 minus small r by capital R2 the whole to the power 1/3. So that is 6 is the actual velocity profile, 1/6. So this is 1/3 into 2 pi r dr. Am I right? Yes, I guess this is the thing. Okay, so again, what is that? So it is 2 pi, so 2c square by r, so 2c square by r2 square into integration 0 to r2 1 minus small r by capital R2 the whole to the power 1/3 into r dr. Okay, that should be the correct integral. Fine. Okay, so let me move on. That value of this integral, so I need to get this integral. So integral 0 to r2 1 minus small r by capital R2 the whole to the power 1/3 into r dr is equal to I don't know whether it is possible to show you that how these integrals looks like. So this integral is something around 9 r2 square divided by 28. I guess this is what this integral is all about. Okay, again I will just box it. Future events. Okay, so then what is beta 2? Then beta 2 c square by r2 square into 9 r2 square by 28 is equal to 18 c square by 28. So it's depends on the relationship what is the value of c. Okay, so what is the value of c? So the in generally the momentum correction factor for turbulent flow is something around, okay, the momentum correction factor in turbulent flow is something around 0.01 to in between 0.01 to 0.05, something like that. So based on that we can choose a value of c actually. So 18 to 1.3, let's say 28 0.6, 18 into 1.2. Yes. Yeah, so let us consider that c is nearly equal to 1.26, something like that. Okay, so 18 into 1.26 square 28, 1.02 1.020. the so which is something around 1.0206, something around that. So this is the momentum correction factor at the outlet. This is the question number 6. Fine. Okay, now let me go to the important part, I guess. Neglecting any pressure or viscous effects, compute the force acting on the duct due to momentum exchange only. Use the integral relationship. Okay, so here I need to use the Reynolds transport theorem, which I discussed in the very first class. Okay, let me go to the Reynolds transport theorem, the integral form. So this Reynolds transport theorem, the question number 7, let me Reynolds transport theorem, or RTT, which I discussed in the very first class. So what it says in case of, so let me first write down the general equation. So it's usually say that like a rate of change of the quantity which I am interested in, that is d n, let my n is the quantity, so dn dt of the system is equal to, what will I have, that is dou t of the integration over volume eta rho dv, so v with a cut is representing volume, plus so plus integration over the, so this is over the control volume, this V, and this is over the control surface, let me write it as CS eta rho V relative dot n cap, that is the unit vector at the surface, into dA. Okay, where A is the like cross section through which the flow is flowing. Okay, cross section through which the flow is taking place, that's my A. Okay, that is the control surface. So as I derived that, so these actually relate the rate of change in the system, like the control system and the like the it's actually represent the rate of change of the parameter in terms of what is happening in a control volume. Okay, so for momentum equation, for momentum conservation, rather I should write, for momentum conservation, n is equals to m mass into velocity, and eta is equals to n by m, that is the quantity per unit mass, that is the V. Okay, so eta is equals to V for the momentum conservation equation. Now what is dn dt? That means d dt of mv system, which will have dou t. So here in this case I will assume that the everything is in steady state. Okay, so this term, or rather I should say that this term is 0 because steady state. Fine. So what I am having, that the rate of change of momentum of the system is equal to integral over Cs, eta is equals to V, so that is my V vector. Okay, so I should write it as in vector notation, I should write it. Okay, here that the control volume have no velocity with respect to the flow, that means the relative velocity between the control volume and the fluid, like it's a stationary control volume. Okay, so that's why here the V relative is equals to V into n cap into dA. So this is what the equation is. Okay, so that is the rate of change of momentum. Means now let me attach a coordinate system with this, that will make more sense. So here let me attach a coordinate system, that is x and y. Okay, so this is how the Reynolds transport theorem is, and for the steady case with stationary and non-deformable control volumes, I can write it as this. Okay, so the rate of change of momentum is equals to the force acting on the system. Okay, so force will have two components, one is the Fx force along the x-axis, let's say that is fx ex cap plus fy ey cap, okay, is equal to, so here this integral I have to evaluate at the inlet and at the outlet, okay. So that is equal to, so v dot n, so let me first do that at the inlet. So at the inlet the velocity is along the positive x direction and v dot n is equal to -1 because n is the unit normal, so n is in this direction, that is the direction of n cap here, and that is the direction of n cap here. So v dot n is equals to -1 here, and v only have the velocity. So let us first evaluate the integrals in only considering the average velocity. Then to do the actual velocity, we just need to add the momentum correction factor. Sorry, we just need to multiply the momentum correction factor accordingly at the inlet and the outlet. So that will give us the correct answer. Okay. So fxex plus fyey. So this quantity at the inlet will be negative. What is v? No, it will be v average 1 into ex cap, okay, okay, that is the first term, into rho into v dot n is equals to, that minus sign I already taken care of, and v dot n is also v average this thing, so it is v average square into dA. What is dA? Into dA, okay, plus at the outlet, what will be this quantity at the outlet? V dot n is positive and v dot n equals to +1 in fact. What is v? So v has both x and y component. It is vx cos theta and vx sin theta, where theta equal to 30 degree, okay. So what will be this quantity then? So it will be, let me write it down, it will be a rho, it will be rho v average at section 2 square, okay, into cos theta ex cap, fine, plus, so this is integration over area rho. So right now for the calculation we are neglecting the momentum correction factor, rather we, so in the latter case we have to just multiply the momentum correction factor accordingly at the inlet and the outlet. So this is rho v2 square sin theta, sorry, that will be dA here, sin theta dA into ey cap. So now what is fx from here? If I compare force along the x-axis on the both side, so fx, and this entire term is constant except the dA, so it will be just the multiplication with the cross sectional area, because I took the average velocities, okay. So it will be rho v average at 2 square cos theta, okay, into pi by 4 d2 square minus rho v average 1 square into pi by 4 d1 square. So that will be the force along the x-axis. What will be Fy? Fy will be rho V average 2 square sin theta into pi by 4 d2 square. Okay, now so what will be this quantity? So Fx, let me calculate it. So let me see where they have neglected. So that is the question number 9. Let me first solve the question number 9 instead of question number 7. Let me first calculate the question number 9. So the question number 9 here, so the Fx is equal to, so it is pi by 4 into density is 790 into, so it is velocity square. What is the velocity? It is 17.684. okay, into the density is also there, sorry, into diameter is also there, 0.06 square, okay, into cos 30, I guess, cos 30 degree, minus, so rho into pi by 4 I took common, so it is 6.366 into 0.1 is the diameter there. That's all, right? So if you do that, it will come something around 353.489 Newton. In the similar case for the problem number 10, which is the Fy is calculated to be 5 by 4 into 790 into 17.684 into 0.06 square into sin 30 degree, which will come something around 349.261 Newton. Fine. Now come to the problem number 7. Then we will see the difference. So if I add the momentum correction factor, what will be the Fx equation with momentum correction factor? With momentum correction factor, Fx will be equal to beta 2 multiplied with this rho V average at 2 square into pi by 4 d2 square into cos theta minus beta 1 into rho V average at 1 square pi by 4 d1 square. That will be the velocity component, like that will be the force. So beta 1 and beta 2 are multiplied because of the momentum corrections factors, okay, and these come out to be something around I guess, let me write it down, it will be 287.4 449. Fx is equals to 287.449, this much of Newton. What is for the problem number 8? Fy will be multiplied by only with beta 2. So this is beta 2 into the same quantity. So it is beta 2 into 349.261. So it is 1 point, what is beta 2? I calculated 1.0206 0206 into 349.261. It will be something around 1.0206 into 349.261, 356 is something around 356.45, this much of Newton. So that's an interesting problem actually. If no one has solved it so far, you should solve it. So yeah, now let me go to the other problem, that is the problem number 11. What it says, kinetic energy correction factor at the inlet. So momentum correction factor is actually affecting the forces, that is the momentum equation. Okay, kinetic energy correction factor at the same time will affect the like the energies. So it will appear correspondingly in the left hand side and the right hand side of the Bernoulli's equation. If you write the Bernoulli's equation at the inlet and at the outlet, it will appear accordingly. If you use the average velocities to like calculate the different heads and all, if you use the average velocities, then in order to correct the actual kinetic energy corrections, like the actual kinetic energy by integrating the velocity profile and all, that means that V by V average Q into dA divided by A. In order to do that, you have to accordingly multiply the kinetic energy correction factor at both sides. So let me calculate the kinetic energy correction factor for the inlet. Okay, so the kinetic energy correction factor at the inlet, what will be that? So the kinetic energy correction factor at inlet, we'll call it as alpha 1. So what will be that alpha 1 here? So let me go to the kinetic energy correction factor at the outlet. So it will be 2 into this thing, so it will be 2Q, right? So is equal to 1 by A1, that is the area at 1, integration over area into V1 divided by V average at 1 Q into dA, right? And this V by V average at section 1 is equal to 2 into that part. So what will be that? And 1 by A1 equals to 1 by pi R1 square. into integration will be integration 0 to r1. There will be an 8 into 1 minus small r square divided by capital R square, tar cube, okay, into 2 pi r dr. That's the area element. Okay, so what is that which is coming here? Pi 2, so it is 16 by r1 square into integration 0 to r1, 1 minus small r square divided by capital R1 square, the cube, into r dr. Now this integral here has the value r1 square by 8. Okay, this integral here has the value of r1 square by 8. So how much is this which is coming? 16 by r1 square into r1 square by 8, so that is equal to 2. So the kinetic energy correction factor in case of laminar flow is something around 2. Now let's go to the problem number 12, which is the kinetic energy correction factor at outlet. Alpha 2 will be equal to 1 by pi r2 square into integration 0 to r2. You will have c cube, that is the relating the maximum velocity and the average velocity, into 1 minus small r by capital R2 the whole raised to half. I think it will be cube, means it will be half, okay, into 2 pi r dr. So what is that which is coming here? So it is 2 c cube by r2 square into integration 0 to r2 1 minus small r by capital R2 whole raised to half into r dr. Am I right here? Yes. And this integral here, what is the value of this integral here? This integral has the value of 4 r2 square by 15. 4 r2 square by 15. Thus alpha 2 is equal to 2 c cube by r2 square into 4 r2 square by 15. So it is 8 c cube by 15. What was the value of c we considered there? 8 into 1.26 cube divided by 15. Cube 1.066, actually that's what I'm getting. Yes, So this is equal to 1.0668. So that is what the momentum correction factor at outlet 0.02 to 1. Yeah, I guess it is coming in that this thing. This is 2. Now the last two questions is very important. If it is given to you that pressure head loss is 10 meter and frictional including minor losses etc is 1 meter, the height difference between section 1 and section 2 what will be the height difference between section 1 and section 2? So you have to apply the Bernoulli's equation between section 1 and you have to apply the Bernoulli's equation between section 1 and section 2 and then see that like once you have to like in first case you can include the alpha 1 with the v1 square with the v1 average 1 square by 2g term and alpha 2 with the v2 average. So what you need to write, I will just write down the equation, you need to calculate it. So the Bernoulli's equation between 1 and 2. So this is P1 by rho g plus alpha 1 into V1 average 1 square by 2g plus Z1 equal to P2 by rho g plus alpha 2 V average 2 square divided by 2g plus Z2 plus head loss HL. Now for problem number 13 you have to use the alpha 1 and alpha 2. For problem number 14 you don't have to use the alpha 1 and alpha 2. That's all. So that means Z2 minus Z1 or rather Z2 minus Z1 is equal to P1 minus P2 divided by rho g plus alpha 1. Okay, so these also I can write it as 1 by 2g into alpha 1 into V average 1 square minus alpha 2 V average 2 square minus HL. That's all, right? So in problem number 13 you have to take the alpha 1 and alpha 2 as we calculated. For the problem number 14 you can take, for problem 14 I'll just write, for problem 14 take alpha 1 equal to alpha 2 is equal to 1. So that is what you need to solve from yourself and just match the answer. Okay, so we'll stop here today and we will meet in the next week. Fine. Okay, so I guess it's a lot of quantity for this week. Okay, thank you, bye.